Welcome to the series of computer science, and in this course of artificial intelligence, last week we have seen uninformed search techniques of breadth first search and depth first search. Today we will see other uninformed search such as uniform cost search, depth limited and iterative deepening. And before we move on, this was a question from the last time where the question was asking for a function to be returned on depth first search. So, this is one of the example that is given here, and this slide is an answer to the question of function on DFS. And if you could see, the function starts with DFS with goal with the root and goal. So, we are giving what is the root of the node and goal that is available to that function, and we are initializing a stack, and within the loop right here, within the loop we are popping the root initially, taking the node value of it and getting the parent, and the same data structure is being used where with the path is defined within this dictionary, and at each point, because it is a stack, and when there is a stack of variables that are there, the first one, if it gets popped, that is being checked as a goal which is at the step, and if it is a goal, it is found, it returns the goal as well as the path right here. If not, the child nodes are pushed one after the other, like in the last example we said first was the right node and in the left node. So, these are the program syntax of it, and this program essentially is written with Python. So, this was the answer to the question, and before we move on to our next section, we will see a quick review of BFS and DFS, and a quick revision on DFS. This is again the same question that we saw in the last class, the same example, where if we take this node, the first root that we visited right here, and if we talk about the previous example, the function right is right to the root node is pushed first and then the left node. So, this 3 is pushed first, then 2 at the top. When it gets popped in the next loop, this is in the second iteration, this 2 is getting visited here. So, this proceeds until we get this path. This is the final path, and once we get this final path, it is actually 5 to 1, and we reverse this so that we get as 1, 2 and 5. And this is an example from the book of Russell and Norvig, where if we see the number of depth, this is d is equal to 0, d is equal to 1, d is equal to 2 and d is equal to 3. There are the level of depth is 3 here. So, in BFS it starts with 1, proceeds with to the left and right, and if you could see, it is proceeding to the left and right, then goes to the depth, next depth level, it visits all these nodes and goes to the other level right here. So, this uses queue. In DFS, this is the next one where it goes in this fashion. First, this gets visited right here, then after B it checks for D, and D is popped out, and this uses the stack, and D, from D it goes to H, and from H there is no goal. So, it goes to I, and it moves on, it backtracks, goes to B, then comes down and goes to J, again it goes back, backtracks, goes to A, and the depth first search proceeds in this fashion. The function which I gave in the first or second slide, and if this is the tree, this is how the function, the algorithm would result in. So, today we are going to see the other type of searches called uniform cost search, depth limited and iterative deepening. So, we will start with uniform cost search. So, here this is an example of a simple tree with, so far we have seen there is no edge cost. If you see the previous slide, here there is no edge cost, the edge is just there is no cost in here, whereas here we are going to bring in some kind of cost with respect to the edge. Okay. So, assume that this is a distance from A to D is a distance, and we are always worried about the minimum distance possible, means if it is minimum distance, that is the path that can be chosen so that we can reach that point faster. So, in that sense we can see the uniform cost search having a minimum cost level. So, that is our goal. So, if A is the start point and D is the goal, what would be the minimum distance that it would take from A to D? Okay. And for this to function, we are going to use the priority queue. Remember, for queue we have used BFS, which is breadth first search. Here we are going to put a priority, and that priority is going to be in terms of minimum cost of edge. So, how it would pretty much function for this example is, we will start with A. At A, there are two children possible, one is 5, another one is 10. The minimum cost here is going to be 5. So, it picks up the edge 5 and that results in B, and at B there is no other path except it is at 3. So, 5 plus 3, it is going to be, the cost is going to be 8, and the path is going to be A, B and D. Now, how is this different from BFS? Before we move on to the other search, we will see the performance of the uniform cost search. Here we could see that it is complete. The reason is, it is very similar to that of BFS, and why it is similar to BFS I will talk in a minute. And it is complete because if there is a goal, definitely there is a way to reach towards the goal. So, it is actually complete. Time complexity, here it is going to be 1 plus C divided by epsilon, where C is going to be the optimal cost and epsilon is the minimum cost edge. Like if you take in this example, the optimal cost, based on the optimal cost by the minimum number of the minimum cost edge. So, this will approximately give the depth that is going to be traversed from start to the end, and that is the reason it is 1 plus C divided by E. Now, a quick question is, when will 1 plus C divided by epsilon will be equal to D? So, this is equal to D when there is no cost, when there is no cost within the edge, but among the edges, in the edges, then it is actually, it is equal to D, which means O of B power D, which is equal to O of B power D, and this is very similar to that of BFS. So, that is the reason why we say when UCS is corresponding to BFS, it is the same as BFS, except that UCS has a cost involved. So, that is regarding the uniform cost search. Now, we will see one more example, and this is again example from the book of Russell and Norvig, which we are always referring to that in this course. Now, this is an map from the map, part of the map from Romania, where the city starts here. I am just going to call the city as S, and this the place here as B, capital B, and there are other places like R, F and capital P. Suppose if we take uniform cost search and we start at, this is going to be our starting point, which is S, and reaching goal at B. So, at this point S, there are two parts, one is going to be R, another going to be F, and from R we are going to have P, and from P it is B, from F it is again B, and if you see the cost for each one of it, from S to R it is 80, that I have written it here, and S to F it is 99, and R to P it is 97, and F to B it is 211, and this is 101. And if you check, if you add these costs, this path is going to be minimal, and this is being indicated at uniform cost search. Now, coming to UCS, how is it related at S? Because of the priority queue with the minimum distance, I am going to choose 80. This is minimum, within 80 and 99, this is minimum. So, the paths will be S, R, which is 80, and from R there is no other path, then it is going to be P, which is again from R to P it is 97, and from P to B it is 101. So, if we add, this is going to be 278, and if we are going with the other path, this is going to be greater than 300. So, this actually uniform cost search is pretty much optimal. So, this example suggests that it is somewhat optimal, it is better than BFS. We will move on to the next search, which is the depth limited search. Again, this is an uninformed search strategy. Depth limited, as the name indicate, it is very similar to that of depth first search, but we are going to limit the search with respect to a limit. This limit is going to play a big role here. And what we will do is, apart from, see, for the function, if you remember the function that I talked in slide 1, we had the function call with the root, the goal. Now, along with the root as well as the goal, we are also going to mention the limit inside the call. And for this example, the example given as A is starting point and G is the goal, and here the depth limit, if I say D is equal to 0, D is equal to 1 and D is equal to 2, the depth limit is 2. So, and we know that by some means, so how the question is, how do we know that the goal is there in the limit 2? Again, by some intuition or by some experience, we know that the goal is available in this limit. Then we can specify this limit within the program, and this program will go recursively until from D is equal to 2, then it will go to D equal to 1, check for goal, and again go to D equal to 0, and it will check for goal. At each point in time, recursively, when it goes back to the parent, it does a depth first search. So, the points to be remembered here is it's recursive, and it is going to be a depth first search, and this is somewhat faster than DFS. The reason is, it need not go through the entire path. Suppose the goal is somewhere there here, that is the one disadvantage here is, suppose the goal is here instead of here, and we say D is equal to 2, it will give it as a failure. So, that is one disadvantage here. So, all these will talk about the performance. So, coming to the performance, the time complexity is order of B power L, where L is going to be less than D. L is nothing but the limit that we specify. If D is equal to 4 and we know the goal is there available as L, then I can say L is less than D. This is the time complexity, and space complexity is B multiplied by L. Why? Because we have to store only that particular, suppose the goal is right here, A, D and G, we have to store that part of the information in the information of nodes in the memory. So, it is going to be B multiplied by L. Completeness, as I said in the previous slide, it is no, because if the goal is somewhere here and if we specify the limit to be at within this structure, then the goal will not be found. So, it is actually not complete, and optimal, it is no, and it does not guarantee the least cost solution. So, that is regarding the third search technique. Coming to the next search technique, is the iterative deepening. This actually combines both depth first search and the breadth first search, and it is very much similar to depth limited, except that we are going to iteratively increase the limits. That limit earlier we had put it as 2. Now, what we are going to specify is at each limit it will increase and until the goal is going to be found. So, this is an example that I am going to give in the next slide, where we are going to increase the limit iteratively from 0 to 3. And if you see in the first limit, and this is an example given again in Russell and Norvig, assume that this is a binary tree where we have A, B and C. And in the first limit you could see that it is progressing in this direction, it is actually a BFS search. Now, coming to the next level, in the next limit where d is equal to 1, 0, 1 and 2. So, it slowly progresses from 0, 1, and if you see at this end all the nodes are getting visited, but no goal is found. In the third limit, when we move, and this is going through each while loop. So, when limit is equal to 3, you see how it proceeds. Earlier it went until this point, now it goes here. The black ones are the ones that are visited, and once it is visited it goes back, comes here, it visits, then it goes here and visits, and then comes here, visits, and it moves on. So, this is an example of iterative deepening. The points to be remembered here is it is a combination of BFS and DFS. Another important point is it iteratively increasing the limits, increase the limits to find the goal. Now, talking about the performance of this search, it is very similar to that of, actually this is going to be order of b power d. There is a slight mistake in this presentation, it would be order of b power d. This is a typo. Space complexity also is order of b power d, and completeness it is yes, of course, because it is very similar to that of breadth first search, and optimality yes if step costs are identical, otherwise it is not. So, that is regarding the iterative deepening. Now, talking about the summary of the entire search, except this bidirectional we will see in the next session. Now, talking about the other 3, the performance of other 5 searches. If you check the breadth first search, it is complete, uniform cost search is complete, depth first it is not complete, depth limited it is not complete. Again I said the reason, it is because maybe of the loops that is there, and iterative deepening it is complete, and bidirectional we will see in the next session of how it is being complete. So, wherever there is depth first search it is not complete, the reason is there may be loops in the depth first search, that is number 1. Other one is the infinite depth, if there is a goal we may not be able to find. Then the time complexity, if you see for each of the searches, for breadth first search it is b power d, and uniform cost search it is very similar to that of BFS, except that we have the cost associated with this, and depth first is b power m, where m we call it as d, the b power d. If d is equal to m, then it is b power d, the maximum depth. M is going to be the maximum depth here. Depth limited is L, where L is less than or equal to d. Remember, we are specifying the limit at the beginning of the session along with the root as well as the goal. Then iterative deepening, it is the same as the breadth first search. The third performance measure, the space, BFS, uniform cost search are going to be the same, yeah, and the iterative deepening it is actually b multiplied by d, and in the last previous thing I said it as b d. The space complexity is b d, because yeah, this is not b power d, this is actually b order of BD. The reason is we have to store only that point of the node inside the memory, the other things can be deleted off. So, it is actually order of B multiplied by D. So, the iterative deepening is order of B multiplied by D, which is very similar to that of depth first search if M is equal to D, and in bidirectional it would be D power D. Again we will see about that in the next session. And optimal, wherever there is depth first search, it is not optimal, the other cases are optimal. Now, in the next class we will see the other uninformed search of the bidirectional search, and I will also give an introduction to informed search technique and the heuristics of heuristics introduction and how it is going to be used in the search technique. Thank you.